Welcome back as we discuss the procedures for the measurement of pulse width and duty cycle, a measurement often required in the field of digital electronics. For a test signal, we'll use a square wave or train of DC switching pulses derived from the signal generator. Notice that for a given time during one cycle of the waveform, the pulse is on, and for the remainder of the cycle, the pulse is off. The on time is called the mark, and the off time is called the space. The relationship between the mark and the space is called the mark-to-space ratio, which is expressed as either a ratio or duty cycle. The scope allows us to determine this ratio by accurate measurement of the two pulse widths. To measure the length of the mark, superimpose the top edge of the pulse on the horizontal center line. Position the leading edge of the pulse on a convenient vertical line. Count the number of divisions from the leading edge to the trailing edge of the pulse. Now count the number of divisions between the trailing edge of one pulse to the leading edge of the next. This will be the duration of the space. The mark is 2 divisions and the space 6 divisions. The mark-to-space ratio is therefore 2 to 6, or more conveniently, 1 to 3. The duty cycle calculated as a percentage is 2 over 6 times 100% equals 33%. This means that the pulse is on for 33% of the total time and off for the balance of the period. When working with pulse, digital and switching circuits, a knowledge of rise and fall time is often required. Collectively termed transition time, this measurement defines the time taken for the leading edge of the waveform to rise from 10% to 90% of its value, and the trailing edge to fall from 90% to 10% of its value. Let's demonstrate the measurement procedure. Set the input coupling switch to AC. Adjust the time per division switch to display about 2 cycles of the pulse, and ensure that the horizontal time base is calibrated. The selector switch must be in the calibrate position. Center the trace using the vertical position control and adjust the volts per division control to fill the screen. Careful observation of the graticule will reveal 2 horizontal dotted lines marked 0% and 100%. Using the variable volts per division control, adjust the amplitude of the signal so that the upper and lower edges of the pulses are contained within the 0% and 100% lines. Switch the horizontal magnification control to ×10 and align the leading edge of the space to the 10% marker using the horizontal position control. Count the number of divisions from this point to a point where the trace intersects with a 90% graticule line. Multiply the number of divisions by the time per division setting. The calculation is 2 divisions times 0,5 microseconds per division, which equals 1 microsecond. However, we are not quite finished, since ×10 magnification has been applied to the time scale, which means that the time per division reading must be divided by 10. Therefore, the rise time equals 0,1 microseconds, or 100 nanoseconds. The same procedure is used to determine the fall time of the waveform, but in that case, examine the trailing edge of the signal. This completes part 2 of this series. Join us again in part 3, where we will discuss dual channel operation of the oscilloscope.